Okay, in this lecture, we're going to cover the second part of our section 2.4 material on the cross product. So in this first part of the lecture, we're going to introduce something called the scalar triple product and look at some applications. So let's start with the definition. The scalar triple product of the vectors A, B, and C is an operation that we can perform on these three vectors, which is defined as follows. It would be the dot product of the vector A with the cross product of the vectors B and C. So this operation on three vectors is referred to as the scalar triple product. And it gives us back a scalar, a number, since it's defined as the dot product of two vectors. Now, we could go about calculating this scalar triple product directly from the definition by first finding the cross product of two vectors, say B and C, and then taking the dot product with that third vector A. However, the following theorem gives us an easier approach to calculating this scalar triple product. So let's take a look at what this theorem says. It says that the scalar triple product of the vectors A, B, and C, which are three-dimensional vectors whose components are known, is given by the determinant of the 3x3 matrix formed by the components of these vectors. So that is, our scalar triple product of A, B, and C is given by the determinant of the 3x3 matrix whose first row consists of the components of our vector A. The second row consists of the components of the vector B, and our third row consists of the components of C. So taking the determinant of that 3x3 matrix will give us this scalar triple product. So let's look at an example of this. Here we're asked to calculate the scalar triple product A dot B cross C, where A, B, and C are the vectors given here. So let's take a look at this. Using our new theorem, this scalar triple product of A, B, and C can be given by the determinant of the 3x3 matrix whose first row would be 2, -4, 1, the elements of A. The second row would be 0, 3, -1. Those are the entries of B. And our third row would be 5, -3, 3, which are the components of our vector C. So taking the determinant of this 3x3 matrix, we would have the entry 2, our first entry along the first row, times the determinant of the 2x2 submatrix I get by deleting that first row and first column. So for that determinant, I would have 3 times 3, which is 9, minus -1 times -3, which would be +3. So that is 9 minus 3. And then I would take the negative of the second entry in my first row. So the negative of that -4 would give me a +4 times the determinant of the 2x2 submatrix I get by deleting that row and column, which would be 0 times 3, or 0, minus -1 times 5 is -5. So 0 minus the -5, or 0 plus 5. And then I would add the third entry along my first row, which is 1, times the determinant of the 2x2 submatrix I'm left with after deleting the first row and third column, which would give me 0 times -3, which is 0, minus 3 times 5, which would be 15. So here my 0 minus 15, and let's see what we're left with. We would have 2 times 6, or 12, plus 4 times 5 is 20, And then plus 1 times negative 15 is negative 15. So altogether, I'm left with 17. Okay. So calculating the scalar triple product of three vectors can be found by taking the determinant of the 3 by 3 matrix that has these vectors as its rows. So let's consider an application. In our next theorem, we get a formula for the volume of a parallelepiped. So let's consider what a parallelepiped is and see how this scalar triple product of vectors is related to its volume. So here, let's first consider what is a parallelepiped. So let's suppose that we're considering the parallelepiped determined by the vectors A, B, and C. So I've given a figure below this theorem to illustrate what we're talking about. In my initial figure, I was using vectors U, V, and W. Let me just rename these as I have them in the theorem, A, B, and C. So if we draw the representations of these three vectors such that they all have the same initial point, well, we can see that the vectors A and B form a parallelogram in some plane, and the vectors A and C form another parallelogram. So the one formed by A and B was this parallelogram below. The one formed by A and C was shown here, and then B and C form a parallelogram in some other plane. So if we think about the region of space defined by those three vectors, we have a shape which is referred to as a parallelepiped, and it's defined by these three vectors A, B, and C. So if we're interested in determining the volume of this region, we would say the volume of that parallelepiped determined by these three vectors is the magnitude of the scalar triple product. So that is, the volume is given by the absolute value of the scalar triple product of these three vectors. So in general, when we calculate a scalar triple product, we could get a negative number. So the volume of this figure is taken as the absolute value of that scalar triple product, since volume must be positive. So let us consider the following problem. We are asked for the volume of the parallelepiped determined by the vectors A, B, and C, whose components are given here. So using our new theorem, well, we know the volume would be given by the absolute value of the scalar triple product of these vectors. So let's start by calculating that scalar triple product. That is A dot B cross C, which, using the previous theorem, can be calculated as the determinant of a 3 by 3 matrix whose first row is the vector A, 2, 1, negative 1, whose second row is B, 3, 0, 1, and whose third row is C, 0, 1, 1. So taking our determinant, we would start with the first entry along our first row, which is 2, times the determinant of the 2 by 2 submatrix that we get by deleting that first row and column. So that determinant would be 0 times 1, or 0, minus 1 times 1. So we get 0 minus 1. Then we would take the negative of the second entry in my first row. So I'm going to have a negative 1 times the determinant of the 2 by 2 submatrix I get by deleting the first row and second column of this matrix. So I would have 3 times 1 minus 1 times 0. So that gives me 3 minus 0. And then I add the last entry in my first row, which was a negative 1, times the determinant of the 2 by 2 submatrix I get by deleting that first row and third column. So I would have a 3 times 1 minus 0 times 0. So that would give me 3 minus 0. So let's see what we're left with. We've got a negative 2 minus 3 minus 3, which leaves us with negative 8. So for the volume of the parallel pipe bed, we would take the absolute value of this scalar triple product. So the absolute value of negative 8 here gives us positive 8 cubic units for the volume of the parallel pipe bed in question. Okay. So the next thing that we'll talk about in this lecture, which is the last part of our section 2.4 material, is another application of the cross product in physics or engineering in defining torque. So let's consider the following problem. Suppose that we are tightening a bolt by applying some force to a wrench. So this will produce some turning effect, which we refer to as torque, and it's denoted in our course as a bold-faced tau. So torque is a vector. It is some quantity that has both magnitude and direction. And this turning effect, which we refer to as torque, is acting along the axis of the bolt in order to move that bolt forward. So we've got a picture here. We've got a bolt, which is being tightened by some wrench. So here the vector from the center of our bolt out to the end of the wrench. So this is defining the length of our wrench, is denoted as R. And then on the end of our wrench, we're applying some force, F. So it's representation shown here. And of course, this produces a turning effect, which we call torque, which would be the vector acting along the axis of our bolt. So if we're curious about the magnitude of the torque, so what is the magnitude of this rotational effect that's being applied, or that is resulting from applying a force to the end of this wrench. So we could say the magnitude of this torque vector will depend on two things. The first would be the distance from the axis of the bolt to the point where the force is applied. So that is the length of our wrench, the distance from the axis of our bolt to the end of our wrench where this force is being applied. So here that would be the magnitude or the length of this position vector R. And the second thing that the magnitude of torque depends on would be the scalar component of the force F acting in the direction perpendicular to R. So let's see if we can evaluate or express what exactly we're referring to here. So we have this position vector R, which is defining the length of our wrench, and there's some force F, which is being applied to that wrench. So what we're interested in finding is the component of this force vector that is acting in a direction perpendicular to our wrench, or to the vector R. So we know there's only a turning effect if we're applying a force in some component that's perpendicular to our wrench. So what we're interested in is the magnitude of this vector shown here, which would be the scalar projection of F onto this vector illustrated in red. So let's see if we can find this. So here, if we think about extending the vector r to define some line, we can see that the angle between the vectors r and f would be theta. So another way to see that, if we draw the vectors r and f such that their initial points are the same, the angle between them is what we're calling theta. So it follows that this interior angle of this little right triangle must also be theta. So let's see if we can use that to determine the magnitude of this vector shown in red. So here, if I were to take sine of this angle theta, well, we can see that there's a little right triangle being formed by that angle theta here. So sine of theta, defined in terms of the sides of that triangle, would be the length of the opposite side here, which is what we're interested in. Let me maybe call this quantity L or something, divided by the length of the hypotenuse of this triangle, which would be the magnitude of that force vector F. So solving for L, this quantity we're interested in, we would have the magnitude of F times sine of theta. So going back to our part 2 here, the scalar component of the force F in a direction perpendicular to R, which would be the scalar projection of F onto this vector, which is perpendicular to R, is the magnitude of F times sine of theta, where theta is the angle between the vectors R, defining the length of our wrench, and F, our force vector. So we will then define the torque as the cross product of R and F. So looking back at our diagram here with the wrench, if we were to draw the representation of our force vector F such that it has the same initial point as the vector R, if we take the cross product of R and F using the right-hand rule, we see we produce this torque vector tau shown in red. So here, our definition for the torque vector tau is the cross product of R, the vector giving us the length of our wrench, and the force vector F. In which case, the magnitude of the torque vector is the magnitude of the cross product of R and F, which in the first part of the section 2.4 lecture, we said is given by the product of the magnitudes of R and F times sine of theta. Okay. So let's look at some problems involving torque now that we've defined it as the cross product of a position vector and this force vector. So here we're told that a bolt is tightened by applying a 40 Newton force to a 0.25 or 1/4 meter wrench, as shown below. So we're asked to find the magnitude of the torque about the center of the bolt. So we're given a little diagram here. So we know that the magnitude of our torque vector depends on a few things. First off, the magnitude of our displacement vector R, which would be given by the length along our wrench. So I'll call this R. And we can see that the length of our wrench is given as 0.25 meters. And it also depends on the magnitude of our force vector, which is illustrated here. We had a 40 Newton force, which was being applied to the end of this wrench. in a direction 75 degrees from the line formed by that vector r. So, using our discussion of the magnitude of the torque vector above, we said the magnitude of this torque vector, tau, is given by the product of the magnitudes of the displacement vector r and the force vector F times sine of theta, where theta is the angle between these vectors. So here, the magnitude of r would be the length along our wrench, which was 0.25 meters, or 1/4 meter. And the magnitude of our force vector was 40 newtons. And then we have sine of the angle between these vectors, which is 75 degrees here. So let's see what we're left with. We have 1/4 times 40 would give us 10 with a unit here of Newton meters, and then times sine of 75 degrees. Now 75 degrees isn't a particularly nice angle from which we could get an exact value using the unit circle, but if we make use of a calculator, we find that this is 9.66 Newton meters, or if you prefer Newton meters, we could also refer to as joules. So here we would have the magnitude of this torque vector as approximately 9.66 joules. So let's consider another example involving torque. In this last one, we are asked to calculate the force required to produce 15 Newton meters, or 15 joules, of torque at the end, or at an angle of 30 degrees from a 150 centimeter rod. Now here, one thing that we want to be a little careful about in these problems is making sure that our units are consistent. So something to watch out for here, we're looking at a 15 Newton meter torque, and the length of the rod was given in 150 centimeters. So to be consistent with our units, we might convert this 150 centimeters to meters. So here, just so we don't forget about this later in the problem, 150 centimeters would be 1.5 meters. Okay, so let's take a look at this. Using the formula for the magnitude of torque that we've just derived, the magnitude of the torque vector tau would be given by the product of the magnitude of r and the force vector times sine of theta, the angle between them. So what we want is to produce a 15 Newton meter, or 15 joule torque. So the magnitude of this torque vector on the left-hand side of the equation is our 15 Newton meters. Now that's equal to the magnitude of r, which is going to be the length along the rod, or this wrench, which was 150 centimeters, or to be consistent with our units, 1.5 meters, times the magnitude of our force, which is what we're interested in. We want what is the force required to produce this desired torque. And then times sine of theta, the angle between these vectors, which was given as 30 degrees. So let's take a look here. We have 15 Newton meters is equal to 1.5 meters times the magnitude of our force vector times sine of 30 degrees, which would be 1/2. So let's see if we can solve for the magnitude of this force. So the first thing I might do to get rid of the factor of 1/2 on the right-hand side, I could multiply both sides by 2. So I would have 30 Newton meters. is equal to 1.5 meters times the magnitude of our force. So to solve for the magnitude of our force, I would have my 30 Newton meters divide by 1.5 meters. So we see that the unit that we'll be left with is newtons. So here we have 30 divided by 3 halves, which would give us 20 newtons for the magnitude of this force. So we need to produce a 20 Newton force at an angle of 30 degrees from this 1.5 meter rod to produce the desired torque.